Okay, hello everyone. You're either watching this because you've missed the live lesson, or you couldn't make it at that time, or because you're going back over it to know even more. Maybe you just got an interest in chemistry. Just a reminder that at the moment, obviously during lockdown, getting hold of a new book if you need one, and most of you will for chemistry, for example, if you're just starting this topic. People were asking how they get hold of a new book. Well, what we've arranged is every Friday afternoon from 3 p.m. until 3:30, down at the main car park entrance, you'll be able to collect a new book. So there'll be somebody down there at that temporary reception area by the barrier in the main car park, the end of the school furthest away from McDonald's. So if you go down there, you'll be able to collect a new science book, a new periodic table, the same for your other subjects. If you need books for other subjects, you'll be able to collect them too. Okay. Secondly, after each of the lessons, whether it be a live lesson or a recorded lesson, what you need to do is submit a photo of your work. Now, what would be great is if you just took a photo and then inside this task, the assignment on Google Classroom, there's a section up in the right hand corner up here, and it says there about adding or submitting work. So once you've attached a file, you can attach a photo of your work, or if you've done it on computer, you can attach a file, be it a Google Doc or a spreadsheet or a PowerPoint. You can always attach work and submit it, and then that will get straight to me. Irrespective of if you're doing the recorded or if you're doing the live, please send me a photo or evidence of every piece of work. Then what I'll do is I'll come back to you, sometimes with brief comments, sometimes with a bit of guidance, especially if I spot that you've made a mistake or missed something really vital out. It's really important that I give you that feedback and that we don't get gaps in our learning. Okay, so today's lesson. Last lesson we looked at the atom, so we're going to do a few recap questions first, and then we're going to move on to what was Ernest doing with the gold foil. And this is one of the scientists from last lesson. This is Rutherford, and Rutherford was the guy who discovered the nucleus. That idea that all the information is, all the weight and mass in an atom is packed into a small area in the centre, and that most of the atom is empty space. Before we move on, there are some questions for you to try. Just quick recall from the other day. Do you remember these? So I'll literally, 4 quick questions. You need literally a minute and a half maybe. So if you pause now until you've got those, and I would say write the question, then the answer. So then when you're looking back at this in your book, it's going to be really useful when you come to revise and for your future reference. No point just on a list of answers. So question and answer, write them down. When you're ready, press play again and then carry on. Okay, I'm assuming you're ready now. What's the plum pudding model of the atom? Well, if you remember, the plum pudding model was that idea that this sphere, this atom, is a big ball of positive charge, and embedded in there are some negative charges, like plums in its pudding, or as I've used before, like chocolate chips in a chocolate chip cookie, and the cookie itself would be the positive charge, the chocolate chips would be the electrons, the negative charge. That's that one. Give yourself a tick if you've got it. What charge is attracted by a negative? And the answer is positive. So give yourself a tick if you've got that. What are the names of the famous chemists who developed the atom? So what we did last lesson, if you try and remember, we did don't try remembering boring chemists. That is Dalton, Thomson, Rutherford, Bohr and Chadwick. And then this last one, what did Bohr's atom look like? Well, by the time they got to Bohr, we had the idea that the nucleus was a little bit in the centre with all the mass in it. Don't need that on. And what Bohr did was, he's the one who discovered the evidence behind the fact that around the outside of an atom we've got these shells of electrons. So electrons, negative charges, you draw them as circles or dashes, whichever, crosses sometimes. So we've got these electrons orbiting around the outside. So his looked like a nucleus in the centre, and then that round the outside. Okay, there with the answers anyway, but I can't help but explaining them. We'll move on. So, Rutherford, he is most famous not for being black and white, because they even had colour in those days, but he's most famous for his gold foil alpha particle scattering experiment. Doesn't really easily roll off the tongue, but if you remember the gold leaf or gold foil, gold leaf is something that they used to decorate picture frames with, etc., because gold is a metal that if you keep rolling it thinner and thinner and thinner and thinner, it's a metal that you can roll incredibly thin, so it's just a few atoms thick. And that way you can make gold go a long way. And what they used to do with old pieces of wood and wooden picture frames is put gold leaf on them, and even on furniture and stuff, and it made the wood look really, really expensive. So a lot of gold picture frames you see actually aren't made of gold, they're made of wood or another material covered in gold leaf. Now, what Rutherford did was he took some atoms of gold leaf, very thin, and then he threw particles at them. So to try and explain this, before Rutherford we had this idea of atoms, and I'm just going to draw a single layer here of gold atoms going down the page. Chemical symbol on your periodic table for gold is Au. So on the periodic table, if you found it, Au is gold. And there's a single row of atoms going down. If there was another row of atoms behind it, I could draw them here. In a solid structure, nice and regular, etc. So, what was before Rutherford was the idea of the plum pudding. So, for example, big area of positive charge, little negatives inside it, and the mass was all spread out. So actually, if you threw something heavy at it, and what Rutherford did was he used a radioactive isotope. Now, you'll be able to make more sense of radioactive isotopes once you've done some physics, which doesn't come till later on. But basically, radioactive materials give out little particles, and one of these particles is called an alpha particle. So this radioactive source over here, so I can have my little box with a radioactive element inside it. Obviously it wouldn't be this size compared with these atoms, and it's going to send out little particles called alpha particles, and it's going to send out these alpha particles at a really, really high speed. And what should have happened? Well, according to the plum pudding model, with that positive charge all spread out, these should have just gone straight through, no problem. Alpha particles would have just gone straight through, having no problem passing through this thin layer of atoms. So they would all have passed through, no issues whatsoever. Did that happen? No. What did happen is this. Lots of them went straight through, no difference there. Some of them were deflected, and if they went here, for example, they might be deflected a little bit. If they went here, for example, they might be deflected a lot. And that's how Rutherford worked out that actually there must be something positive in the centre of an atom, because these other particles, these alpha particles that are positively charged, were moving away from something. The second thing he discovered, and I'll try and do it in a different colour to make it even clearer, some of the particles actually bounced back, but not many of them. So, for all the particles going through, now and again, one would go in and come smacking back out. So, his second bit of evidence was that this area in the centre is very dense. It's packed with all the mass. So it's positively charged and it's hard. But actually, so what Rutherford had proven was he'd proven that all the mass in an atom, so there's his first bit of proof. Number one, all the mass is in the centre. Number two, the fact that most of the particles went in. Number two, most of an atom is empty space. And number three, the centre of an atom has a positive charge. Now, if you've understood that and you've made sense of that diagram, starting from plum pudding, I'd start to write some notes and some diagrams. So if you go with before Rutherford, we had, so I'll put an A up here, that's where we start, the plum pudding model. B, what did we think would happen? We thought they'd all go straight through. Number 3, what did happen? These green lines, some bounced off, but lots went through. Number 3, sorry, not 3, C. And number 4, or D, sorry, what are the conclusions that we came to? All the mass is in the centre, is positively charged, and most of an atom is space. Pause for as long as you want to do that. I'll come back to this one in a minute if it makes more sense to you. This is the sort of equipment. He had a detecting screen around the outside that can detect where the particles end up. Really thin gold foil. And here we are. Here's our beam of alpha particles hitting the gold foil. And as you can see here, lots going straight through. Some being deflected a bit, deflected a lot, and now and again over here, particles bouncing back, exactly as I just said. Again, if that's a diagram that's useful to you. And here's a summary of both. So this is pre-Rutherford. This is Thomson's plum pudding model. And now here we have post, after Rutherford, we've got this idea of a nucleus in the centre. These two diagrams definitely please draw, because this was a major change in our understanding of the whole of, well, of atoms, but in fact, because every single thing ever is made up of atoms, it's changed our understanding of how anything works in chemistry. And these are sort of some prepared slides. So this, not to repeat the same thing, this is what would have happened. Here's an alpha particle. Here it is going straight through according to the plum pudding model. Is there anything on there that you haven't got in your notes yet? If not, move on. And here's what did happen. So, what have we got? The atom paths were deflected and bent, just like here. That means there had to be positive charge pushing them away, repelling them. Then you've got other ones that actually bounced back off the centre, like here, because of this dense amount in the centre. And because everything was in the centre and not around it, that's why they decided that the nuclear model was a better model than the plum pudding model. And that's what we still work on today, the nuclear model. And so to the last bit. Two diagrams. The plum pudding diagram and the nuclear diagram. And what do? You label these labels onto those diagrams. So I'll just take one for example, this one here, the spread out positive charge. Ah, that was this model, the spread out positive charge was the grey area. This one down here at the bottom, the deflected path, what does deflect mean? Ah, that's where, here for example, the positive one, it's deflected downwards. It's been changed direction by being repelled away from the nucleus, the positive one, but it's changed direction. And then the second task, summing up what we've done today, in 3 points, can you explain Rutherford's work? I'm not going to do it for you. I want to see what you've written when you send me the photo of your work. And then last thing, just make sure you're really clear what conclusions can be drawn. That's going back to a few minutes ago. What did Rutherford prove? What were his conclusions? One of them, for example, was that most of an atom is made of absolutely just blank space. So, when you've completed that, obviously stop. You are done for the day. Or sorry, not for the day, you've done for this lesson. What I'd like you to do is take a photo of your notes from today, and I can have a look at your labels for these bits, etc. And then please, can you send that to me? Thank you.